Dr. Greenhouse, you have the floor.
Okay, is my slide up?
No.
Oh, yeah. Oh, so do I have to share?
Yeah,
Yep.
we have to do it
Okay.
again.
Yep.
Okay.
There we are. Perfect.
Do you see a cover slide now?
Yes,
We do.
Okay, great. Well, thank you everyone for tuning in to hear about the James Webb Space Telescope. Let's see why I'm not. Please stand by. I'm not able to advance my slide for some reason. I'm going to stop sharing and share again. See if
Okay.
that helps. Okay, great. Okay. Well, space telescopes are astronomers' primary tool for looking back in time. Traveling back in time is the stuff of science fiction, but looking back in time is science fact, and this is much of what we do in astronomy today. And it's made possible by the finite speed of light. If you look at a person who is perhaps in the room with you today, right now, you're not seeing them as they really are. You're seeing them as they were a few nanoseconds ago. Now, a nanosecond is a really small amount of time. So that transmission delay for the light to get from that person to you is imperceptible. But as we look at objects that are farther and farther away, the transmission delay becomes more pronounced. So for example, if we had a magic switch that could turn off the sun and we flip that switch, it would be 500 seconds would elapse before we knew that anything happened, because it takes 500 seconds for the light to travel from the sun to us. And so when we look at the sun, we're seeing it as it was 500 seconds ago. As we look at objects that are farther and farther away, we are looking literally farther into the past. So for example, if we look at the center of our galaxy, we're seeing it as it appeared 25,000 years ago. And we can use this technique to look back to the earliest epochs of the universe. And that is one of the prime objectives of the JWST mission. The JWST was conceived in the late 1990s as a mission to connect the dots, if you will, between this famous image of the oldest light in the universe and this famous image, which at the time was the deepest image then recorded by the Hubble Space Telescope. This image on the top was made by NASA's COBE satellite, and it looks back to a period in the evolution of the universe when the universe was a few 100,000 years old. And is at that time that the universe became transparent and photons could escape. And this is literally an image of that epoch. And these colored blobs in the image denote small temperature differences in the radiation. And those blobs are the seeds from which galaxies formed. This Hubble image looks back to a time when the universe was about 1 billion years old. And between that epoch and this COBE epoch, shown on this cartoon, there's a mysterious, poorly observed epoch known as the cosmic dark zone. And it's scientifically of great interest because this is the time when the first stars and galaxies formed. And it's very poorly studied because we haven't had the right type of telescope in space to observe that period in the evolution of the universe. And that was one of the major objectives and motivations for the James Webb Space Telescope mission. Now, when Hubble took its that famous image, it did so by staring at a single spot in the sky for a long time, a couple of weeks, leaving the camera shutter open, if you will. And this is the image that was produced. And as you can see, even after that long exposure, there are still lots of very faint red objects still in the image. These are high redshift galaxies, and we have not seen the beginning yet. We have not seen back to the epoch of galaxy formation with Hubble, and we'll talk about why in a few slides. When the JWST mission starts, it will repeat that experiment conducted in much the same way. It'll take a very long exposure of a few fields in the sky, but with JWST's larger aperture, and as we'll discuss, with JWST's infrared capability, we should be able to see back to the epoch of galaxy formation. We should be able to see the first galaxies. Now, when we say JWST will observe the first galaxies, we don't mean that you will pick up a copy of the newspaper and see a picture of the first galaxy. What we mean is shown on this plot. We will make a measurement of the star formation rate as a function of look back time, as a function of redshift. And this plot shows what we know today. But as you can see, at the very high redshift end of this plot, the error bars in this data become very large and there's missing data. And so JWST will fill in the high redshift ends of this plot and allow us to discriminate between various theoretical models of the formation of the universe. Now, this is what you see playing on the lower left of the screen is a supercomputer simulation of the formation of the universe. And as you can see in this simulation, the matter in the universe that we can see, the stars and galaxies are not uniformly distributed. They're distributed in a spider web like arrangement known as the cosmic web. And the JWST will allow us to explore and study how this structure formed and evolved over cosmic time. When we look at galaxies nearby with the Hubble Space Telescope, they have the morphologies or shapes that you're familiar with from textbooks and posters. Some have spiral arms, some have bulges, but they're generally very regular, symmetric morphologies or shapes. When we use the Hubble Space Telescope to look at the most distant galaxies that we can see, we find that they don't look like that. Their morphologies are very irregular. They're sort of beaten up blobs of light. And with JWST, we'll be able to study why that's so. We'll be able to study why the common morphologies of galaxies change over cosmic time. With Hubble nearby today, we see lots of irregular galaxies that are the result of galaxy collisions, we believe. This is a computer simulation of a galaxy collision. And with simulations like this, we're able to actually reproduce those irregular morphologies that we see nearby with Hubble and with large ground-based telescopes. And we think that in the early universe, collisions like this happen more frequently, and that this is perhaps the reason why a lot of the primeval galaxies have very irregular morphologies. But with JWST, we'll really be able to explore this across cosmic time. Now, you've all heard it said that space is expanding. What do we mean by that? What we mean by that is shown in this cartoon, which is a cartoon animation of a piece of raisin bread dough that's set out to rise. And imagine that you are sitting on one of the raisins while the dough is rising. What would you see? You would see all the other raisins moving away from you, even though you are not at the center of the expansion. And you would see that no matter which raisin you chose to sit on. And this is a good analogy for what we believe is happening in real life. When we say that space is expanding, we don't mean that the objects are flying through space like an explosion, but rather that the space itself is expanding like this raisin bread dough. Now, when JWST looks back at the primeval galaxies, those first galaxies to form after the Big Bang, the galaxies emit their light in the ultraviolet part of the spectrum. But while that light propagates through the expanding space, through that expanding raisin bread dough, its wavelength is stretched into the infrared. So to observe those galaxies today, we have to observe in the infrared part of the spectrum. And so the JWST is designed with infrared capability. So what is the infrared? Light comes in an infinite range of wavelengths, from extremely short in the gamma ray, X-ray end of the spectrum of wavelengths that we see light taking on is called the electromagnetic spectrum. And at the short end, we have ultraviolet light. Our eyes can't see ultraviolet light, but that light can burn our skin if we stay too long at the beach, for example. Our eyes are only sensitive to a very narrow slice of this spectrum. And that's because only a very narrow slice of that spectrum can propagate through the Earth's atmosphere to reach the surface. And so our eyes are evolved to match that transmission window in the Earth's atmosphere. Just longward of that visible light window, we have the infrared part of the spectrum. And our eyes can't see the infrared part of the spectrum, but our skin can feel it. If you hold your hands near an electric stove burner, the burner can be black, but your skin will sense the heat from the burner. Your skin is literally sensing the infrared light emitted from the stove burner. And so it goes. The wavelength of light can become very long in the microwaves that you might use in your kitchen and radio waves that you might listen to in the car. The Hubble Space Telescope is designed to operate in the visible part of the spectrum and in the ultraviolet. The JWST, the Webb Space Telescope, is designed to operate in the red end of the visible and in the infrared part of the spectrum. So the Hubble Space Telescope lacks the infrared capability needed to see those first stars and galaxies, and the JWST is optimized for that. And the infrared capability of the Webb is useful for lots and lots of other science. One area of other science that the JWST will focus on is how stars and planetary systems are formed. This is a famous image taken by the Hubble Space Telescope at something called the Eagle Nebula. The spaces between the stars in our galaxy, the so-called interstellar space, is not an empty vacuum. It's filled with giant clouds of molecular gas and dust. And this image of the Eagle Nebula is an image of one such giant molecular cloud. You can see these pillars here are pillars of molecular gas, and mixed with that gas is a lot of dust. And so that's making those pillars opaque. However, if we observe that same field in the infrared, the longer wavelength infrared light can see through the dust and get a much better view of star formation that is occurring in these giant molecular clouds. These giant molecular clouds collapse onto themselves and due to self-gravity. And as they do that, the pressure inside the cloud becomes very, very high. And as that pressure becomes high, the gas gets hot, just as it would if you were filling a bicycle tire at the gas station. The tire gets warm when you fill it. Same thing happens in the cores of these clouds, only in this case, it gets really, really hot to the point where nuclear fusion begins. And this is how stars are formed. Now, when stars are formed, we find that they are typically surrounded by disks of material, circumstellar disks, as they're called. This is material that is literally left over from the star formation, and it forms this disk-like structure. And those disks are of great scientific interest because that is where planetary systems are formed. And the Webb telescope will be studying lots and lots of these circumstellar disks to better understand how planets are formed and how things like our solar system form and evolve. This is an artist's conception of the debris disk around our own star, the sun, shown alongside an actual map of where that debris is located. These chunks of debris, the so-called trans-Newtonian objects or Kuiper belt objects, are of great scientific interest because they are literally chunks of material, primordial material left over from the formation of our solar system. And we've put special non-sidereal tracking capability into the JWST to enable it to observe these Kuiper belt objects and the planets of our own solar system. Now, we recently went out and visited a Kuiper belt object in NASA's New Horizons mission in 2014. The main objective of the New Horizons mission was to fly by Pluto. But after we flew by Pluto, we sent it on to this Kuiper belt object to take the first ever picture, close-up picture of a Kuiper belt object. And this is what we saw. And it turned out to be two smaller objects stuck together. And this is very exciting. It's of great scientific interest for folks who model the formation of planets via agglomeration of smaller particles. And this particular object has been modeled, a computer simulation here, showing that a very low velocity collision can cause these objects to stick to each other without either object being destroyed. And JWST will study many of these Kuiper belt or trans-Newtonian objects. Now, JWST will also study the planets of our solar system. It will study Jupiter. It will help us explore Jupiter's great red spot, which, as many of you know, is a storm that's raged there for more than 400 years. And today we know that spot is shrinking. And so with JWST, we'll hopefully explore why it's shrinking and why it's red. We still don't know why the great red spot is red. And the Webb will also search for small moons of Saturn that were too faint for flyby spacecraft to have seen. Now, liquid water in the solar system is not limited to the Earth. Moons of Jupiter and Saturn, particularly Europa and Enceladus, are believed to have vast oceans that are enclosed by a crust of ice. And geysers have been observed by the Cassini spacecraft erupting through this crust of ice on Enceladus. And this is of great interest because it's possible, very possible, that life could exist in those oceans. We know from studies of the mid-Atlantic ridge at the bottom of the Atlantic Ocean that life can exist there without sunlight on chemical energy. And it's possible that life exists in these oceans. And so JWST will study these geysers to learn more about their chemistry and what they contain. This is an actual Cassini spacecraft image of water geysers erupting on Enceladus. All right, now, when I was a graduate student, there were no planets known outside the solar system. But today we know that essentially all stars have planets. And so there are literally billions of habitable worlds in our galaxy. We don't know if they're inhabited, but they are habitable or should be habitable. And we have now learned how to search for life on them by studying their atmospheres with space telescopes. And so the search for extraterrestrial life is no longer the stuff of science fiction. It's a major science objective of NASA. And the search for life is very much on, and JWST will be an important part of it. So JWST will study the atmospheres of exoplanets, planets that are orbiting stars other than our own. It will use spectroscopy to probe the chemistry of those atmospheres. With spectroscopy, we can spread light out into its component colors so that we could see the emission or absorption of individual atoms and molecules. And by comparing to laboratory spectra, we can actually identify the atoms and molecules that are producing the emission or absorption. So we can literally measure the chemistry of these exoplanet atmospheres. Shown here is the spectra of Mars, Earth, and Venus. And you can see, and say in the case of the spectrum of the Earth, that there are all these bumps and wiggles in the spectrum. So the spectrum is a plot of brightness versus wavelength. And you can see all these bumps and wiggles. And those are all due to emission and absorption by molecules in the Earth's atmosphere. If the Earth had no atmosphere, this would be a flat line. And so by recording spectra like this on exoplanets, we will be able to study the chemistry of their atmospheres to search for chemistry that wouldn't be there without biological processes. We'll be searching for what are called biomarkers, chemical species that would be unexpected without biology. Now, how do we really do this? The main way that the JWST will do this is something called transit spectroscopy. And how it works is shown in this cartoon. In many cases, we will be observing the exoplanet system edge on, or nearly so. So when we point our spectrometer, we point our telescope at the star, and a planet wanders into our line of sight between our spectrometer and the star, we take a spectrum. And so what are we getting? We're getting a spectrum of the star plus the spectrum of the planet. Now we just wait a little while for the planet to move out of the way, and we get a spectrum of the star by itself. We subtract the two, and we are left with the spectrum of the planet's atmosphere. And this has been done many, many times with the Hubble Space Telescope, and it's become somewhat of an exact science. And JWST will spend a lot of time making observations like this of exoplanet atmospheres. And JWST can detect water on an exoplanet that's just a few times the size of the Earth. Why do we care about water? It's not because alien life might become thirsty and need something to drink, but rather for the organic chemistry of life to occur on a planetary scale, we need a liquid solvent on a planetary scale, and water is what we're most familiar with. All right, now when we first put pencil to paper on what type of telescope did we have to build to do all that science, we realized that we needed about 7 times the light gathering capacity of the Hubble Space Telescope. And in order to see those primeval galaxies, which are very, very faint. And we also needed a Hubble's ability to see fine detail, angular resolution, as they call it. But we needed that angular resolution at a longer wavelength. We needed it in the infrared part of the spectrum. And that also necessitates a large mirror. And as I mentioned, we needed to design a telescope that had capabilities spanning the optical to the mid-infrared spectrum. So as soon as we realized this, we realized that we had 2 big problems that almost stopped the project dead in its tracks. In order to get that light gathering capacity and angular resolution, we needed a mirror that was bigger in diameter than the biggest rocket. That was problem number 1. And in order to observe in the infrared part of the spectrum, the telescope has to be made very cold. And this is because any object above absolute zero emits light. If you were to put infrared goggles on, you would see the walls and floor of the room you're in glowing. You would see your body glowing in the infrared. And if we didn't make the JWST very cold, it would be blinded by its own infrared self-emission. And we found that we had to make it very, very, very cold, almost minus 400 degrees Fahrenheit, or about minus 200 degrees Celsius. And there is no mechanical refrigerator, even today, that is powerful enough to cool something as big as the Webb telescope to such a low temperature. So those are the 2 problems that had us stumped for a while back in the 1990s. But we did solve them both so that the mission could proceed. So let's take a look at how we solved them. First, let's take a look at how we solved the cooling problem. The Webb will not be placed in orbit about the Earth the way the Hubble Space Telescope is, but rather we will put it at a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And this point is about 1.5 million kilometers, or about 1 million miles in the anti-sun direction from the Earth. And so how does that help us cool the telescope? Well, you can see that in this configuration, all of the sources of heat on the Webb telescope, the sun, the Earth, and the moon, always lie in one direction. So we realized that if we could deploy a giant sunshield so that the telescope would always live in the shadow of the sunshield, we determined that it would cool passively by simply radiating its energy away to the cold darkness of space. Now, to be a useful telescope, we have to be able to point it all over the sky. And so to make this solution work, we had to figure out a way to keep it in the shadow of the sunshield and at the same time point it all over the sky. So we designed a sunshield that was big enough so that we could point the JWST 5 degrees toward the sun and 45 degrees away from the sun, and it's still in the shadow. So now we've covered an arc on the sky that's 50 degrees. And if you look at this diagram for a minute, you can see that we could rotate the JWST about the Earth-Sun line, and that won't spoil our shadow situation at all. So now this arc becomes an annulus, that covers about 35% of the sky. And so at any instant in time, JWST can point at 35% of the sky and always be within the shadow of its sunshield. Now, as the Earth and the L2 point, this whole pattern of Lagrange points, orbits the sun, now we're rotating about this axis. And so one can see that this annulus will cover the whole sky every 6 months. So every 6 months, JWST can observe any spot on the sky and while remaining continuously in the shadow of its sunshield. And so that's how we solved the cooling problem. Now, we don't put JWST exactly at the L2 point. And the reason for that is we have to stay outside of the Earth's shadow because we are generating electricity with solar arrays. It takes about 2 kilowatts of electricity to operate the JWST. So we put the JWST in an orbit about the L2 point. And this libration point orbit, as it's called, is unstable in the direction of the Earth-Sun line. And so it has to be maintained by station-keeping thrusters. And the propellant for those thrusters is tanked up for about 10 years of operation. So the JWST mission can last at least 10 years, possibly much longer than that, depending on how efficiently we are able to operate the JWST. Now, there's one other feature of the L2 point that makes it ideal for our mission. As the Earth orbits the sun, the Lagrange point, of course, follows the Earth around the sun. Normally, if you were to place an object farther from the Earth than the sun, it would orbit with a longer period. But the L2 point is special. It orbits the sun with exactly the same period as the Earth. And that means that the telecommunications range between the Webb and the Earth will remain constant no matter how long the mission lasts. And that is important for our ability to get the data back from the Webb. All of the data that the Webb collects is transmitted back to the Earth via radio transmission. And so having that range be constant greatly facilitates that. Okay, so how do we solve the mirror being bigger than the rocket? We adopted something called a segmented mirror architecture so that we could literally fold the telescope up inside the rocket. So the Webb's mirror is made of 18 hexagonal hexagonal mirror segments. So we really have 18 telescopes. And these mirror segments are mechanized in 7 degrees of freedom, the 6 you're familiar with, plus radius of curvature, so that they can all be finely adjusted so that they play together as if they were one big mirror. We'll be flying the JWST on a French rocket called the Ariane 5. And the Ariane 5 has a 5-meter diameter fairing. So the JWST is designed to fold up and fit within that fairing. This is an end view, and you can see there's not much extra space in that fairing, but it all fits in there. And the Ariane 5 will not be launched from Florida. It'll be launched from Kourou Launch Center in French Guiana. French Guiana is on the east coast of South America. The whole payload weighs about 6.5 metric tons. In the next slide, I'll show you how the JWST unfolds from the fairing. And the origami that you will see involves 40 deployable structures and 178 release mechanisms, every single one of which must work perfectly for the JWST to be successful. And unlike Hubble, the astronauts can't go to the L2 point. So it's very, very important that everything work right the first time, because if it doesn't, there's no way for anyone to travel to the JWST to fix it. So let's take a look at how the unfolding occurs. The first thing that happens is the solar array comes out, and so that we can become power positive, we're operating on batteries up to this point. And there are a few mid-course correction maneuvers, rocket firings that have to occur to put us on course to the L2 point. There you see the high gain antenna come out so that we can begin communicating with the Webb telescope. In here you see pallet structures unfolding. Those pallet structures have that giant sunshield folded up inside them. And here you see a deployable mast extend to provide thermal separation between what will be a very cold telescope and what must remain a room temperature spacecraft. And now these mid-telescoping booms are pulling that sunshade out of the pallet structure. And these spreader bars at the edges will separate it into the 5 layers that are needed to give it the thermal performance that's necessary. A trim tab deploys to help us with the trim of what is a giant solar sail. And there are various other small deployments that occur. There are other small thermal radiators that deploy for cooling certain parts of the JWST. And here you see the secondary mirror of the telescope deploying. And now you see the wings of the primary mirror deploy, much like a round drop leaf kitchen table. And that's how the origami works. Now, the Webb mirrors, those 18 hexagonal mirror segments, are not made of glass. They're made of a material called beryllium. Why did we choose beryllium? As the Webb slews across the sky to visit various objects, there will be thermal gradients formed in the mirror. And we don't want those thermal gradients to spoil the figure of the mirror, the shape of the mirror. And so we had to find a material that had a very low coefficient of thermal expansion at the extremely low operating temperature of the JWST. And beryllium has that needed property. The beryllium starts out in a powder form, and we compress it under great heat and pressure to a block of material called a billet. And then after we go through all the trouble of making that block of material, we machine almost all of it away. This is the back of the mirror, and this is the front of the mirror. You see laboratory equipment reflected in the front of the mirror here. And we do this because in anything that flies, whether it's an aircraft or a spacecraft, weight is really a premium. It's a driving engineering requirement to minimize weight. And the figure of merit here is aerial density, mass per unit area. And the JWST mirrors are about 6 times lighter than the Hubble Space Telescope mirrors in that metric, in aerial density. And they represent the state of art in lightweight mirror segments. Now, if you're thinking ahead, you realize that we have yet another problem. How do we polish mirrors? We polish mirrors by rubbing on them with gritty stuff until they get smooth and shiny enough. But mirror polishing is a room temperature operation. And so if we polish the mirrors at room temperature and then use them at minus 225 Celsius at 50 degrees above absolute zero, that means that we have to polish in the wrong shape at room temperature in order to get the right shape at the extremely low operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so to make the Webb mirrors, we had to follow an iterative process whereby we would polish the segments partway and then put them in a specially instrumented space simulation chamber at Marshall Space Flight Center in Huntsville, Alabama. And this space simulation chamber is a big vacuum vessel whose walls are lined with shrouds that are cooled with liquid nitrogen and liquid helium. So we can simulate both the vacuum and the low temperature of space. And we would put the partially polished mirror segments in that chamber and observe them with special test equipment to see how the mirrors, the actual mirror performance was tracking to our model. And then we would have to go back to the polishing house and iterate around this loop until became into spec. And what was shown here in the upper right is actual data. This is the ambient surface figure of one of the mirror segments and how that figure changes when we cool it to the operating temperature. So this was a very lengthy process, but all this work is behind us now and was all done successfully. Now, in addition to making the mirrors, we had to design a structure to hold those mirrors. And the requirements on the structure are really, really daunting requirements. The structure has to hold the mirrors and withstand the huge accelerations, the huge mechanical loads that are associated with the rocket flight into space. And it has to withstand nearly 300 degrees of temperature change from room temperature to the operating temperature. And it has to do all that and at the same time hold all the mirrors in just the right position to within a small fraction of the wavelength of light. So we had to invent a composite material that could meet this requirement. And we did that. And this is a picture of the actual flight structure. And this structure involves more than 3,000 individual composite parts that have to be, in effect, glued together into a very precise mechanical system. This is a walkout deployment test of that structure. Here we're walking out that secondary mirror deployment that you saw in the video. Engineering is very much an empirical science. And so this is just an example of some of the kinds of testing that we need to do to really understand how our designs work and to ensure that they will work in space. This is a robotic pick and place machine that we designed to help us mount the mirror segments on the backplane structure of the telescope. These are the actual flight mirror segments. They look black because there's a to keep the mirror surface. What you see here is a robotic arm that has a very high precision end effector that allows us to very precisely locate the mirror segments on the structure. And this is shown here happening in a clean room at Goddard Space Flight Center, Greenbelt. You get the idea. This is a typical craning operation, also at Goddard, that just gives you a sense of how we handle the JWST telescope in the clean room. And here technicians are putting it on a turnover fixture to get ready for some testing. The people that you see in the clean room dressed in those white suits, bunny suits as we call them, the people are the dirtiest thing in the clean room. That clean room is cleaner than a medical operating room. And that is just some of the difficulties in building systems like this. Okay, let's talk a little bit more about that sunshade. The JWST sunshade has an SPF of 1,000,000. So if you had this on the beach, you'd be very, very well protected. It is literally the size of a tennis court, 73 by 40 feet wide. And it has 5 layers that give it that SPF of 1,000,000. It's made of a heat-resistant plastic material called Kapton. The sun-facing surface is coated with silicon, so it actually looks pink in real life. And all the remaining layers in the opposite surface of that first layer are coated with vacuum deposited aluminum. And as you can imagine, the hot side, the sun-facing side, is pretty hot, 85 C, and the cold side is very cold, minus 200 C. Now, the sunshade has to have this curved shape, and that's very important to ensure that light doesn't reflect off the sunshade and get into the telescope. And those of you who sew may realize that in order to make a curved shape out of flat cloth, you have to have lots of seams. And each one of these layers is actually a quilt of 50 pieces. And there's about 7,000 inches of seaming for putting that quilt together. In this case, it's not done with needle and thread, but rather with thermal spot welds. And the seams have to be very, very accurate. And so the building of the JWST sunshade was a major technical challenge, but all of that work is behind us now. The sunshade was one of the most difficult engineering challenges in the whole project. Here is a deployment test of that sunshade, and here we're testing how we fold it and pull it out of those pallet structures that you saw unfold in the animation. You can notice a person in the center, so that gives you a sense of scale here. This thing is really enormous. And if you look closely, you can even see the quilting. These tables, these mylar covered tables, are there for gravity offloading. So they're not there in space, but we need them to be there for this testing on the ground. And this is happening in a clean room at Northrop Grumman Aerospace Systems in Redondo Beach, California. Okay, let's talk a little bit about the science instruments that are located at the business end of the telescope. The job of the telescope is to collect the light from the faint objects that we're observing and then image direct that light into the science instruments. The science instruments will do a little bit of processing on that light, and then will convert the light to digital signals that can be transmitted to the Earth. And these are Webb's four science instrument systems. This is the NIRCam instrument. I guess you'll be getting a talk from one of the scientists in the NIRCam team later in the summer. This is the main near-infrared camera on the JWST. So this is the instrument that will observe those first galaxies to form after the Big Bang. And it was made by the University of Arizona with their contractor, Lockheed Martin Advanced Technology Center in Palo Alto, California. This is the NIR-SPEC instrument. It's the main near-infrared spectrometer on the JWST. It's a very unusual instrument. This instrument is made of an advanced ceramic material called silicon carbide, and it is the first true multi-object spectrometer to fly in space. What that means is that this instrument is designed to obtain spectra of 100 objects simultaneously and keep all those spectra separate. And that was an important requirement for the JWST because those faint galaxies, they're very faint. And so it takes a long time, long exposures to obtain spectra of them. And if we had to observe them just one at a time, we wouldn't be able to get an adequate sample size within the life of the mission. So this instrument was a partnership between the European Space Agency and Goddard Space Flight Center. And it's a very unique instrument, and it'll be key to obtaining spectra of a wide range of objects that JWST will observe. This is the mid-infrared instrument. This is the longest wavelength instrument on the JWST, and it will give humanity its very first high definition view of the mid-infrared universe. It is both an imager and a spectrometer, and it was built by a consortium of 10 European countries and NASA's Jet Propulsion Laboratory. And it was led by the University of Arizona and the European Advanced Technology Center in Edinburgh, Scotland. And this is the fine guidance sensor, which also has a science instrument function. This was built by the Canadian Space Agency. The fine guidance sensor can sense pointing to a millionth of a degree, or about 3 milliarc seconds. So this instrument is what enables us to point the telescope at the objects that we'll be observing. And then the science instrument part of it is optimized specifically to obtain spectra of those exoplanet atmospheres that we spoke of. Now, after we got that, the science instruments integrated to the telescope at Goddard Space Flight Center, then we had to put the whole thing into a specially designed truck-mounted shipping container to allow us to transport it, but at the same time maintain the high cleanliness special environment that the Webb needs to remain, qualified to fly in space. And this shipping container is designed to fit onto a C5 transport aircraft. So we literally drive it onto the aircraft. It just barely fits, as you can see here, but we did get it in there. And we flew it from Andrews Air Force Base near Washington, D.C. to Houston, Texas, in order to do more testing at the Johnson Space Flight Center. Now, at the Johnson Space Flight Center, we did something called an end-to-end optical test. And what that test consists of is exactly what you would imagine from the name. We shined light through the whole telescope system into the science instruments, just the way it will occur in space, to make sure that everything was really working. And this is a test that we did not do on the Hubble Space Telescope program, with consequences that many of you are aware of. And although it's a very difficult and expensive test, we decided not to skip it on the JWST program because, as I mentioned, if things don't work right, there's no way that for the astronauts to fix this one. To do this test, we had to use the largest cryogenic space simulation chamber in the world. It's called at Johnson Space Flight Center Chamber A, and it was designed and built for NASA's Apollo program. This is an image looking through the door of Chamber A, and you can see the Apollo spacecraft and the command module in there. We had to bring this chamber out of mothballs and refurbish it for the JWST. And we were able to roll the JWST into that chamber on rails, and so big is the door of the chamber. And this was the test setup. We had the JWST in the bottom of the chamber, suspended on rods from the top, and we were able to shine light into it and observe the mirror with special optics test equipment to make sure that everything was working perfectly. And we did discover some problems in this test, so it's a good thing that we didn't skip it. This work is all behind us now. And with the completion of that, we went back into the aircraft and then flew from Houston, Texas to Los Angeles, California, where our contractor, Northrop Grumman Aerospace Systems, would then add the sunshield and the spacecraft to the rest of the assembly. Let's take a look at that. This is a clean room at Northrop Grumman. And here you see we are going to integrate the telescope in its stowed configuration to the sunshield, which is in those pallet structures that we spoke of earlier. And the spacecraft is underneath that. You really can't see the spacecraft very well. Now that work is done, but we're not done yet. We still have to test the JWST for the vibration and acoustics that it will experience during the rocket flight to space. So that assembly that you just saw in the video was then put into a vibration chamber. It was put on a vibration table, so it was literally shaken, and then put into an acoustic chamber where it was blasted with loudspeakers. And then we had to do performance testing on it to make sure that we really passed that test. All that work is behind us now. Now, once we have added, because we have added the sunshield and the spacecraft to the assembly, we can no longer put it on the aircraft. And so this time, later this summer, the shipping container, instead of rolling onto an aircraft, it will roll onto this special roll-on, roll-off transport ship. And we will ship out of Port of Los Angeles and travel through the Panama Canal to French Guiana, where it will roll off into Kourou Launch Center to begin integration with the rocket itself.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sunshield ever flown, a 5-layer, tennis court-sized sunshield that blocks heat from the sun, Earth, and moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
Okay, we have young people on the call tonight. You don't need to worry that when the JWST mission is over, we will have answered all the questions. There'll be plenty of questions left for the next generation to solve. Missions like this typically raise more questions than they answer. And what happened before the Big Bang? What's inside a black hole? What is the universe evolving into? Are we alone? So you can join the quest for those answers. The people that do this kind of work, the people that build missions and systems like this come from all walks of life. They are every kind of scientist and every engineering discipline you can think of are needed to do projects like this. Managers, even lawyers are required, and you can be one of them. To be one of them, go to college, study science, engineering, and math, and you'll be well prepared for a career in aerospace. There's a quote that I like to read. The book of nature lies continuously open before our eyes, but it can't be understood without first learning to understand the language and characters in which it's written. It is written in mathematical language, and its characters are geometrical figures. That's as true today as it was 400 years ago when Galileo said it. So go to college, stay there if you're already there, learn that language, and this is a career path that's very practical and doable, no matter what your background is. Those are my remarks for this evening. When Webb flies, we should see the beginning of everything, and you can follow the action at NASA Webb, #JWST. And I'll be happy to take questions for as long as you have them.
Thank you very much, Dr. Greenhouse. That was pretty fantastic. Everyone is muted, I think, except for a few people. So if you do have questions, please unmute yourself. If you do not have a microphone, you can enter your questions into the chat. So with that, let's ask some questions.
I have a question. This is Bob McFarland. I'm just thinking about the tremendous amount of data that needs to be broadcast back to Earth. And I was curious about how many and where are these antennas located that pick up all this information?
Yeah, it's a great question.
The seasons.
We're using something called NASA's Deep Space Network. And those antennas are spread around the Earth in a few locations. And so that we can always have one that will see the JWST. And it won't take continuous communication to get the data down. We need 4 to 6 hours of transmission a day. In the beginning of the mission, we will have continuous communication, and then we'll throttle back if we feel comfortable. But it will be using the Deep Space Network to receive the data, and then it is transmitted via the internet to the Space Telescope Science Institute in Baltimore, Maryland, who will be operating the mission. The data is processed and archived there and then sent on to the astronomers who are conducting the observations, and again, via the internet.
I see. So the antennas are nothing different than what we already have.
Correct.
Oh, that's
Correct.
great. Yeah. So in this world of hacking, is there any risk that all this data could be corrupted?
We use encryption to protect the data.
Oh, okay.
And so we should be in pretty good shape.
I see. All right. Thank you. Let's see. From Sandra. Sandra, do you have a microphone?
Yes, I have a microphone.
Okay. Do you want to go ahead and just
Okay,
speak
I'll
to
say
your
my
question?
question. So the telescope was delayed several different times. Why was the launch date changed so many times? And do you think we'll actually meet the current scheduled launch date?
Okay. Well, we had to invent 10 technologies to make this mission possible. And sometimes technology development takes longer than planned. So there were many, many challenges to face in development of the JWST. This is really one of NASA's most difficult projects, but it's all behind us now, and we are ready to go. The Webb is on track to be ready for launch at the end of October. The rocket is showing up a few weeks late, so the launch is currently planned for the end of November. But we're at the end now. We're in great shape, and the rocket will be squared away. And so we're pretty confident that we'll be launching at the end of November.
Thank you.
Okay, well, there's a question from B&G from Sudbury, Maine, is it? Do you want to go ahead and ask that? Or I'll read it.
Go ahead, Bob.
Oh, okay. It says, thanks for your wonderful presentation. Wondering if you considered other fuel sources besides the sun, nuclear, for instance, and how hard was the decision to leave it unserviceable and as potentially only a 10-year mission due to propellant issue?
Yeah, great question. So solar power is really the lowest cost, easiest way to meet the power requirements. So we didn't consider nuclear, and there's really nothing problematic or difficult about using solar arrays at the distance of the Sun-Earth L2 point. For the very deeper space missions to the outer solar system, they need to rely on nuclear power. Now, for the limited life of the mission, every mission, it's not possible to make a mission that will last forever. The Hubble has lasted a lot longer than its design life, and so we just have to set some limits to have a project of finite cost that can actually be done. And so the engineering design that we adopted in terms of propellant usage is the 10-year propellant that we need for orbit maintenance at L2. But some of our models have that lasting a lot longer. It really depends on how efficiently we are able to be in using the observatory. Now, we have considered and we have studied what a refueling mission, a propellant replenishment mission to the JWST, might look like. As you can imagine, it's very, very expensive. The expense is not small compared to a replacement observatory. And 10 years is a long time to operate in space without servicing. And so the JWST will probably have some other problems by the time it's been out there long enough to run out of propellant. But we did put some reference marks and targets on the observatory that would enable a future propellant replenishment mission to dock to it. But NASA has no plans for such a mission. And we'll just have to, consider that when the time comes. But it may be that simply replacing the JWST with a new system might be a better thing to do scientifically. We'll just have to wait and see.
I don't see any other questions on the chat.
What is the next mission after the James Webb?
Okay, well, the question is, what is the next mission after James Webb? It's a mission called the Roman Space Telescope. It's a very different mission. It's a monolith mirror telescope. So a little bit more like Hubble than like JWST. And it's geared primarily to study dark energy. And it also has studies exoplanets with gravitational lensing, and it develops coronagraph technology for exoplanet studies. But its primary mission is to understand the phenomena of dark energy that's causing the expansion rate of the universe to apparently increase.
One from Uriah to everyone. What was the most exciting moment you felt during this project?
Sorry, what was the most exciting goal?
Moment.
Oh, moment. Wow. Well, the most exciting moment is going to be yet to come when all that origami occurs during the first month of flight and works properly. But for me, getting the instrument module integrated to the telescope and working as it was supposed to, that was the most exciting moment for me personally, because that's the part that I was responsible for from a science perspective. But the real excitement is going to come right after launch, when all that origami you saw in the animation occurs.
All right. From Gagan to everyone, what is the reason behind the golden color of the mirrors?
No, it's a great question. The mirror, why is the mirror covered with gold instead of aluminum, the way most telescope mirrors are? And it's because we're operating in the infrared part of the spectrum. The reflectivity of gold is higher than aluminum for the part of the spectrum that we're operating in. And so gold was the optimal choice of a reflective coating. That's why it's gold. And it's because it's gold that the short wavelength cutoff of JWST is at 0.6 microns. That's where the reflectivity of gold drops. Most optical telescopes use aluminum because aluminum is the best reflector in the visible light band.
That's interesting. Mark, maybe you want to comment on the other chat points.
Sure, Bob, let me see what they are. Hold on just a
Oh, well, you submitted them.
Oh, yeah,
The quest-
yeah, that's
question
what I was
was,
working on.
question was, where can you find the recording of this presentation?
Yep, and
And,
that'll be up on the channel in a day or two. And if you can go to our website, we also have links to them there.
right, and Mark has posted both of those addresses on the chat portion of the Zoom features. Are there any other questions that someone would like to ask
I have one.
Um,
This is Kelly. Just a quick question. How long after launch will we have to wait for data to start coming in?
Okay, how long will we have to wait to see the science? The first 6 months of flight, we're doing all those deployments. We're getting those 18 mirror segments to play together as one, and we're calibrating and commissioning all of the science instruments. So the real science program will begin 6 months after launch. Now we on JWST we are doing something a little bit different. In most of the NASA missions, we have what's called early release imagery, where cool images are released to show that the system works, and so that everybody can really sort of see some product immediately from the mission. On JWST, we decided to expand that, and we'll be doing what's called early release science. So queued up at the very beginning of the science mission are a series of projects that were specifically designed so that the data could be understood and processed, and real science results could come out very quickly. So 6 months after launch, things should be pretty exciting scientifically in terms of results available from the web.
All right, we have a question from Uriah. What data set is the team most looking forward to receiving? Any particular target?
Yeah, there's the team is the whole worldwide astronomical community. So there's lots and lots of answers to that. The cosmology results from JWST should be transformational, as should the exoplanet results, and the results on star formation. And so there's really no unique answer to that question. I think JWST will just be exciting day after day after day. I think it will raise more questions than we can imagine now. What we've seen from the Hubble Space Telescope, we couldn't even imagine at the beginning of the Hubble Space Telescope mission, and Webb will be much the same. So it should be pretty much continuous excitement for as long as the mission lasts.
All right, the question from Gagan. Are the 5 layers of the sunshield placed at equal magnitudes from each other?
Okay, are the 5 layers equal distant? They're at a very precise distance from each other, and the distance changes as you move out in radius from the center to the edge, so that the radiation can escape as it moves out to the edge. Getting the shape right is really key to getting the thermal performance that's needed from that sunshield to enable the JWST to reach its low temperature. So the engineering behind that sunshield was very, very difficult. It really was one of the toughest parts of the mission from an engineering perspective.
All right, I have a question from Jay Dega. I believe that may be a first name is Jay, but Jay Dega. Simple question with likely trivial answers. Would the shadow screen not block the solar panel and the communication path?
Sorry, could you repeat that question?
Sure. Let me get back to it. Would the shadow screen not block the solar panel and the communication path?
Yeah, no, the sunshade won't block the solar arrays. The solar arrays will always have, no matter where the JWST is pointed, the solar rays are articulated so that they will always be pointed at the sun when the JWST is observing. And same for the high gain antenna.
All right, question from Kevin Zhu. Do you have an estimate of the time breakdown in terms of designing and planning, material gathering, processing, and assembly?
Oh, boy. It's been a long project. The project started in 1996. I joined in 97, and we're launching this year. So it's been a long effort, and we just did a lot of hard work every day of that timeline. Some of the longest lead areas were the mirrors and the sunshade. The science instruments were, took many years. This is a pretty tough project. It's really one of the most complex things that NASA has ever done.
But you had to practically invent every component, it sounds like, and also the materials, or many materials.
Yeah, we had 10 specific technologies that we had to actually invent. And that took a little longer than expected. But it was a long haul, and we rewrote some engineering textbooks along the way. So it's been a really interesting project. It's going to enable a lot of other missions beyond JWST, and this is how the space business goes.
All right, well, there's a addendum comment from Kevin. Wow, the telescope is older than me. With a smiley face. Doug Bauer asked, what materials are the support structure made of?
It's a composite material that we really had to develop to meet those requirements that I spoke of. So that whole black structure is a composite, and there are some metal end fittings in the composite. It's for aficionados, it's an M55J composite type material.
Okay, then this is from Felix Luciano. Is there a list of Hubble objects that the James Webb expects to follow up?
Oh, absolutely. Yeah. I mean, many things that the Webb will observe will have been observed by other NASA missions. Hubble, the Chandra X-ray telescope, and so forth, because much of what we learn in astronomy requires observations over the whole electromagnetic spectrum that we spoke of. So quite often, one mission alone doesn't give us as much information as we would get by combining the data from lots of NASA missions. And so, that'll be the case here.
Thank you. David Kabinski asked, what is the propellant used to stabilize the telescope for imaging?
Well, for imagery, the propellant that we use, we're using chemical propellant, so it's hydrazine. It's a bipropellant thrusters for the big maneuvers to get out to the L2 point. And for tiny maneuvers, we use monopropellant. But for the fine moving of the telescope, we use reaction wheels, flywheels, if you will. And by accelerating and deaccelerating these flywheels, or reaction wheels as they're called, we can move the telescope very precisely on the sky.
Wow. All right. Doug Bauer asked, will the James Webb Space Telescope do some long exposure images like the Hubble Space Deep Space image?
Yeah, that's one of the big objectives of the mission. And so it's going to do that pretty early on. And it will be doing that quite a bit throughout its mission, taking very deep exposures to look back in time to the epoch of galaxy formation. So yeah, it will definitely be doing that.
Okay, from Sarah Dixon. This has been a great presentation. Thanks for your time this evening. And I want to echo that too, because you may have wanted to do something else on a Saturday evening.
Oh, it's my pleasure.
Any other questions? All right.
All right. Well, it's been a pleasure talking to you all, and thank you for having me.
Oh, thank you for
All
being
right.
here, Matthew. That was really great.
Yeah.
Thank you very much.
Yeah, thank you everyone for joining. If you'd like to stick around and chat about anything else afterwards, you don't have to leave, and several of us will stick around. But thank you all for joining.
Okay. Bye-bye.
One last one, Matt. Uriah, thanks you for the presentation, and thanks to the Seven Ponds Club for hosting and arranging this great meeting. Thank you from Steve Spinier, here from Irene. So happy to have been invited from South Florida. Well,
Oh, great.
welcome, coming all this way to see it.
Well, thank you to everyone again for coming. It was a very good presentation and audience.
Very good.